Your book uses an interesting approach to finding these two particular limits. And so what they say is that, okay, if you have a polynomial, okay, so let me write this down. So if you have a polynomial, you should remember what those are. If not, go back and look to see exactly what a polynomial means. Because look, if you don't know what the definition of a polynomial is, then the rest of this isn't going to make any sense to you. So if you have a polynomial or a ratio of polynomials, so we call these rational functions. Okay, so if you've got either of those two, first, polynomials are continuous everywhere. So if you've got a polynomial function that's continuous anywhere, we can use direct substitution to find the limiting values, and I'll show you what I mean by that. The second is, if we have a rational function that is defined, meaning that it is not at a vertical asymptote spot, right? So if you remember rational functions, they might look like this, have a vertical asymptote here, come back like this. For every value except for, let's say this is x equals -2. Rational functions are continuous everywhere except where you have discontinuity, which obviously that sounds redundant. It's like yeah, of course not. Rational functions are continuous everywhere where they're defined, meaning where the denominator is not equal to 0. So what we've got here is that rational functions are continuous everywhere that's not a vertical asymptote, and polynomials are just continuous everywhere. So once we know that, once we have that in place, now that can be proven, okay? We're not going to prove that, but that can be proven. So once we have that in place, finding these limits over here are very easy. Watch. For a, I've got a rational function. So what if a function is continuous? If it's continuous, then the following holds. Then the limits as x approaches x naught of f of x is equal to f at x naught. What that means is we can do, if a function is continuous and we want to find its limit, we can do direct substitution as long as the function is defined at that point. So the rational functions, this is continuous as long as when I plug in 2, I don't get 0 out. So let's just check that. If I plug in 2 here, I get 2 squared, which is 4, plus 2 times 2 is 4. Well, that's 8 minus 8. Well, that gives me 0. So I can't do a direct substitution here yet. I'm going to have to do a replacement and then a direct substitution. So watch. For a, the limit as x approaches 2 of this guy is the same as the limit of x. Now we got plus 3 minus 2 for the factors on the top, and on the bottom we're going to have x minus 2 times x plus 4. So we have to reduce that first, and the reason we reduce it, because if we just try for direct substitution right away, we get an indeterminate form of 0 over 0. So this is going to be the limit as x approaches 2 of x plus 3 over x plus 4. Now, since 2 for this function right here is not a vertical asymptote, it means that we can do a direct substitution for this limit, which gives me 2 plus 3 over 2 plus 4. Those are both 2's. So this is 2, this is 3, this is 2, that's 4. So that gives me 5/6. Okay, that's the limiting value. Now what I don't like about this is that to prove continuity, you have to show the limits exist and are equal to the function. So we're going to reverse here. But what we're saying is that, okay, at some point we could prove that all polynomials and all rational functions are continuous except for where the rational functions are not defined. And since that's true, then we can apply this. So let's look at this here for b. So for b, we can factor out a delta x. So this is the limit as delta x approaches 0 of delta x plus 2 over delta x plus 1. And now these are just rational functions. If you don't like the delta x, just get the deltas here and just put x. Put whatever variable you want in there. If look, you can write this like this. The limit as that something approaches 0 is the same as that something over that something plus 1. Plus 2 over that something plus 1 is what I meant to say. So we can do a direct substitution because this is a rational function, and when I plug in 0, I don't get 0 in the denominator. So I'll plug in 0, I'll get 2 over 1, so I'll get a value of 2. So the idea is we can do a direct substitution for polynomials and rational functions as long as they're defined at that x value. So as long as they're defined.